Of my favorite things at the same time, pizza and math. Can't beat it. Okay, let's do a quick part B on this one. This is going to be pretty quick, I think, now that we've checked that something is a subspace. And again, you might have looked at this example and said, oh boy, I don't feel real comfortable with this. Right? You're not necessarily going to go home feeling great about everything. The point is then, now you know what you need to review. So if showing that something is a subspace is a bit of a problem for you, or you just need to refresh, this is one example. Now go home and look at some older examples, some other examples. Okay? Of course, a related question, once you have a subspace, is going to be, give me a basis and dimension for this space. So I would like to do that here. So part B is find a basis and a dimension of S. Okay. So does anybody know how to do that? I'm going to propose a solution. Can I do that? I'm going to propose a solution. You tell me if you guys like this. Okay, if I want to find a basis, I need to bust out the variables and make a list of the vectors. So for a basis, I'm going to take my polynomial. I'm going to bust out the A. I'm going to bust out the A, and then I'm going to, after I bust out the A, B, C, and D, I'm going to make my basis out of what's left. Does that look good? If I was asking you for a basis for P3 of R, which is four-dimensional, by the way, then I would love that as a perfectly good answer. But I'm not asking for a basis for P3 of R. I'm asking for a basis for S. So you've got your hand up back here, Deshaun.
Yeah. We're supposed to, but I think we should make a matrix and then get the null space of the matrix.
So that's always an idea. That's one of the problems in 250B is everything is, oh, put it in a matrix and magic happens and you get your answer. So we tend to get matrix happy around here through a lot of the stuff we learned this semester. Okay, so that's one idea. Put it into a matrix. Does anybody have another? Bilal?
Shouldn't we just substitute 3D minus C for A and then we can bust out the variables?
So we actually already did that right here, didn't we? Right, we already replaced the A with the condition 3D minus C. So A1 became 3D1 minus C1. So actually, what I was doing earlier with busting out the variables on this thing was actually the right general idea. But the problem was I was busting out the variables on a general polynomial of P3 of R. Whereas the question is asking you to bust out the variables, or in other words, find a basis for S. So I just need to make sure I'm busting variables out of the right thing. So what you really want to do, so Bilal is exactly right, what you really want to do is take the condition, A has been substituted with 3D minus C, and then Bx, Cx squared, and Dx cubed, and now you want to bust out the variables. You only have 3 variables now to bust out, right? So I can bust out the B, and it leaves me with x. I can bust out the C, and it leaves me with, there's a -1 right here, and a plus x squared right there. And then I want to bust out the D, and that leaves me with a constant 3 there, and then plus x cubed, right? So these guys then become your basis. Those become your basis. So your basis is, so you bust out the variables, you have x, -1 plus x squared, and 3 plus x cubed. Clear enough? And then, okay, so is everybody okay with that? We don't need to put it into a matrix here. We can actually just leave them as polynomials and work with it that way. And so what would be the dimension of S here?
3.
Right, 3 vectors, so it's 3-dimensional. Okay? That look good to everybody? Let me ask you one more question while I'm at it. Could you convince me, even though we wrote this was a basis, of course if it's a basis it needs to be a spanning set and linearly independent. It's definitely a spanning set because we wrote P of x. Any P of x has been expressed now as a linear combination of these three polynomials, right? So we have that for sure. So it's a spanning set. How would you convince me that these three polynomials are Li? Okay, one good way to do it when you have functions is to use the Wronskian. It's weird because this is kind of a chapter 4 problem, and I didn't teach you guys the Wronskian until chapter 6. But as it turns out, the Wronskian, which involves taking derivatives of whatever your functions are, really would have worked even in chapter 4. I just didn't want to introduce it at that time because there are many places in the material where you can't do a Wronskian to the vectors. But with polynomials, you can. So I can test Li using, so one way to do it is to use the Wronskian. So this is the W thing, right? So just really quickly, let's just do this. The determinant of, can somebody remind me how I build my Wronskian? Exactly. So we just put our original basis vectors, our proposed basis vectors on the top line, and now we just differentiate our way down the matrix. So the derivative of x is 1, and the derivative of 1 is 0. This is going to end up being a 3 by 3 matrix, right? Okay. What's the second column going to be? 2x and 2. Good. And then the third column? 3x squared and 6x. Exactly. Awesome. How do you want to evaluate that determinant? You know what? Just for fun, I mean, frankly, I would probably do it using the arrow method for a 3 by 3. That's just the easiest thing for me. But let's just, for practice, do the cofactor expansion. So imagine you wanted to cofactor expand this. Would there be a good choice of a row or a column to expand? First column would be a good choice. I like that idea. So let's expand the first column. Remember how that works. You basically take each entry in the column, so we start with x, and you multiply it by the 2 by 2 minor that is opposite to x. In other words, if you cross off the first row and column, you get a 2 by 2 submatrix here. And for that, I'm going to use AD minus BC. So I would have 12x squared minus 6x squared. Okay? And then we have a minus 1 times, now I have to cross off the row and column that has a 1 on it. Notice I put a minus. That's because you remember the way that the determinant works is these alternating plus and minus signs when you're expanding. So right now we're expanding the first column. The middle one has to have a minus on it. And what I'm left with is 6x times negative 1 plus x squared minus 2 times 3 plus x cubed. So that's the way that would look. Okay. Might help to just simplify this a little bit. Notice here you have 12x squared minus 6x squared. Well, that's 6x squared, and it's times x, so it becomes 6x cubed. Right, I'll just go ahead and put that down. And then over here, let's see, I have a 6x. There's a minus 1, and there's also a minus here, so it's really a double negative. I'll make that a plus 6. And then minus, here's a minus a 6, an x, and an x squared, so that's minus 6x cubed. Okay? And then I have a minus 6, but there's a double negative again, so it's really plus 6. And then a minus 2x cubed, but there's a double negative again, so it's plus 2x cubed. So there should be some cancellation here and here, right? So we end up getting 2x cubed plus 6x plus 6. Now, as long as you can plug in an x value that makes it non-zero, your vectors will be Li. So I would simply evaluate this one now at any value of x that's not going to give me 0, I could plug in 0 for x if I wanted. That would be the easiest. It just gives me 6, which is not 0. And if it's not 0, then the vectors are definitely Li. Make sense? Okay, great. All right, so we could check it using the Wronskian. This is just a quick review of the Wronskian. Would there be another way? Does anybody have another idea how I could test that these three polynomials are Li?
Put it in the matrix and EROs.
Okay, put the vectors into matrices and use EROs. Right, exactly. So I'll call this one using a matrix. So can you guys help me build the matrix here to test those things for Li? So the first vector is x. How would I put that into the matrix? And how do I put it in the matrix? As a row? As a column, exactly. So 0, 1, and 0. That's because the x coefficient is a 1. The other two coefficients are 0. Right? Okay, good. What about the second basis vector? How would I put that into the matrix?
Shouldn't you have an extra 0 there for x cubed?
Oh, thank you. We actually have an x cubed vector as well, so I need to add another 0. Thanks. Right, so I have a constant. So I'm putting my constant terms on top, then my x term, then my x squared term, and then my x cubed term. Right. Okay, great. So my x coefficient is just a 1. Okay, what about the next column?
Negative 1, 0, 1, 0.
So negative 1, and then 0, and then 1, and then 0. Exactly. So there's no x and no x cubed. Okay, and then what about the last one?
3, 0, 0, 1.
3, 0, 0, and 1. Exactly. Okay, and we augment this with what?
Zeros.
All zeros. When you're testing for Li, you just augment this thing with all zeros. Great. And look at this, guys. Basically, after you do a quick little row swaps, permute the rows, you get pivots in every single column. So pivots in all columns to the left of the bar anyway. That implies no free variables, right? No free variables. So the polynomials are Li. That make sense? Can anybody think of a third way that we could have done this?
Can you also just be observing the basis and looking at it, you see that it's not just even multiple?
Okay. A theoretical way. That's exactly what I was looking for. Sort of a more theoretical way to explain why the vectors are Li. First thing is, now be careful though. Just because three things are not multiples of each other doesn't make them mutually an Li set. The classic example of that is the vector 1, 2, 3, 4, 5, 6, 7, 8, 9. We actually used this example earlier in the semester, and what I said about that is, okay, the first two vectors are not multiples of each other, the second and third vector are not multiples of each other, and the first and third vector are not multiples of each other, but they are still an LD set. Because if you take the determinant of that 3 by 3 matrix, you will get 0. Okay, so be careful. It doesn't have to be that one vector is a multiple of another to say that they are, that could cause them to be LD. They could still be LD even in this kind of situation. But I agree with the overall principle here that I can look at this one theoretically and tell you that these are definitely Li. Why is that? Well, I can certainly say that the first two vectors, let me just write them here. The first two vectors are definitely not multiples of each other. When you only have two vectors, remember that Li really just comes down to they're not multiples of each other for two vectors. It's only when you start getting 3 or more vectors that things get complicated. For two vectors, they will be LD only if they are multiples of each other. And these are not. So these two are definitely Li, right? Now, is there a way of writing the third one? So remember what LD means. LD means you can write one of your vectors in terms of the others, right? That's kind of the theoretical viewpoint of LD. Is there a way of writing 3 plus x cubed, which is our third vector? Is there a way of writing that one as a combination of these two?
No.
As a linear combination? Look at the first two, right? You can never get past x squared. Right? You don't have any x cubes in either of these polynomials to begin with. So this new polynomial that you now have is surely not expressible using the first two. So the first two were Li to begin with, and you've now added a new vector which definitely did not create any linear dependencies. In general, the third vector, when you add vectors, you run that risk, right? You might create dependencies by adding more vectors. But here, the vector you added is a very safe vector. It is not, clearly not, expressible as a linear combination of the first two. So I'm going to avoid writing all of that out. But you can always go back and re-listen to the explanation again. It's basically, the point is just that the first two are Li for sure, because they are not multiples. And then the point is the third one is not expressible as a linear combination of the others. So the set remains Li. The set remains Li at that point. Okay, everybody all right with that? Okay, beautiful. So we have shown, so that's actually this Li bit was actually problem 3 on the sheet. So I've actually done the third problem without even really realizing it. Okay, I'm going to change gears again if everybody's good with that. I'm going to give you another problem to solve. Go back and forth here for a while. Everybody staying awake okay? All right.
With pizza, yes.
The pizza helps, doesn't it? Keeps you going. I got to sleep in a little bit this morning, which was nice. Unfortunately, I have to get up tomorrow at 7 in the morning, so I have a very early morning. But that's okay. I'll be fine. I'll survive. Okay, I'm going to jump ahead on the sheet. I've just done the first 3. I'm going to jump ahead to problem 9 on the sheet here. Number 9 says solve y prime minus 3 over 2x times y equals 6y to the 1/3 x squared ln of x. Okay. And before we jump right into solving it, I want you to take a few seconds to think for yourself about what type of problem this is, where it fits in the material, and what your approach is going to be. So we'll give everybody a little bit of quiet time to think about it. Does anybody think they know what this has to do with? Raise your hand if you think you have an idea where we're going with this. Brian, what do you think?
Separable?
Separable. Okay. I'll let you work on separating it while I take another idea. David? Bernoulli would actually be my choice. Now, some of these problems can be more than one. In fact, it might be possible. So to check if it's separable, you'd really want to write the y prime as dy over dx, and then you'd have to end up moving this to the other side. The problem is when you add the 3 over 2xy to the other side, factoring it is going to be difficult, right?
I realized I wrote it down wrong.
Oh, you wrote it down wrong. Oh, that's always a problem. Okay. Yeah, no, that's fine. So this one is definitely of the Bernoulli type. Now, just remember again, we already wrote this down at the beginning of the review tonight, but I'll just write the form one more time for you here. There are some key things that you need to write down right off the bat. One is, what is the value of n?
It cannot be.
N, well, n could be 1. I mean, what is it here is really the question.
Oh,
It's 1/3. Right, yeah, n is 1/3. Actually, if n is 1, the point is then really you can reduce the problem to a linear equation, but it doesn't matter if n is 1 or not, it's fine. So let's take 1/3 for n. Okay, and can you guys tell me what other equations I might want to write down right away before I forget them?
U equals n minus, or y to the n minus 1.
U
Oh,
equals
1 minus n.
y to the 1 minus n. Let's be very
Right.
careful about that. There's usually at least one person every exam who gets that power wrong. So it's 1 minus n power, right? So this becomes y to the 1 minus 1/3, so it's actually y to the 2/3 power, right? Y to the 2/3. We don't need to use that right away, but it's just good to get it written down, so you can not have to stress about it later, all right? Okay, so that's one thing to write down. What would be the other thing that would be good to write down kind of near the beginning of the process right now? Not ready to write down p of x yet, because there is